Alright, so finally we're reviewing polar stuff for Calc 3 only, but this is all polar, and you better watch those other two videos, actually 3 videos since I split it up. But this explanation is a way to show you how to find the area of a sector. Okay, if you're in my pre-calc class, no, you weren't in my pre-calc class, so it doesn't matter. But in my trig class, I do try to talk about this. Sometimes I have time, sometimes I do not have time. So the way I do this is I try to identify that the areas of a sector and the circle are going to be proportional to the arc length and the circumference. So if we kind of zoom in on that part of it, and please remember the definition of radian measure is up here, and that S is equal to theta times R. Okay, so if you want to find the area of that sector to get a formula for that, then your arc length is S, and you can substitute theta R in place of it from up here. And basically you're going to cross multiply this, and your area of your sector times 2 pi is going to be equal to this, pi r squared theta. And if you multiply by 1 over 2 pi, you end up with this formula. So that's the formula for area of that sector right there. And it's important that you know that so that we can find the area of a polar graph. Just like finding the area of a representative rectangle back in Calc 1, we're going to find the representative polar rectangle. They call this a polar rectangle. I really just call it a sector. But anyway, polar rectangle. If you can't read that, oh well, I'll try it right here. But I'm not going to erase it. It's towards the end of a very long day here so far. Anyway, so you need to remember that when we actually find an area of some kind of polar graph, or between polar graphs, or shared by a polar graph. Alright, so hopefully you all would remember, especially fondly from Calc 1, that we would draw representative rectangles. And what did I always tell you back then when we found that area of that entire shaded region? I'm talking about what's in yellow. Well, we had to figure out what the area of this rectangle was right here. So you just need to remember high minus low. And then this dx is the thickness of that. Now, how is that comparable to our polar sector, or our polar rectangle? So we're looking at this thing right here. And what we have right now, we don't need to worry about high and low. What we need to worry about is the angle measures right there. Okay, that's going to be our one that is a bigger rotation than this one right here. And so when you're worried about your theta, that's going to be your d theta right there. Okay, so that's kind of like your bigger rotation minus your smaller rotation. And then as far as the distance to this point, that's going to be your radius. So if I move this equation up a little bit, what you should see then is there's the area of a sector. It's 1/2 the radius squared, and then the angle for that one representative sector right there, that angle is going to be d theta. And so if you want to sum all of them up from alpha to beta, then you're going to do a definite integral, and that's how you're going to find the area of that shape. So that's what we're going to do right now, is find that area for the next example. Now, this particular problem is one that you're familiar with. Isn't that a nice circle? I'm learning how to use the tools on this thing. Makes me want to throw up. Anyway, we are talking about the area of this shape right here, which you should have committed to memory as a circle. And if you recall, it's a circle with a diameter of 6, and so the radius is going to be equal to 3. And if you go back to general math, the area of that circle is pi r squared, and so you know the answer is supposed to be 9 pi square units. Well, great. We're going to find that as well. but we're going to use this as our representative sector. And so what I would have then is I want to do just half of it. I just want to do the top half, this from here to here. And then I can use symmetry. And you say, why would I want to do that? Well, because if you recall, when I reviewed all that stuff, it only takes half a rotation for you to complete that circle, and some of you might have been tempted to go all the way around to 2 pi, and your answer would have been 18 pi, and you say, well, what did I do wrong? This doesn't work. No, that's not the case. It's because you didn't remember what I reviewed with you, that it only takes a rotation from 0 to 2 pi, or to pi, I should say, in order for you to finish that shape right there. 2 pi is too far. You're going to draw the circle on top of itself. So when I do my formula, I'm going to use symmetry, and symmetry, oh, go away. Symmetry is going to tell me that I have this area and this area doubled. And that's why I made you graph all those things and talk about the things and find points and notice symmetry when we reviewed all of that. I hope you watched it because it made me ill because I had to do some of that twice. But anyway, you have your 1/2, you have your radius squared, you have your d theta, that's your area of your sector, and now we just have to figure this part out. Well, come on now, this isn't that hard. The cosine of 0 is going to give you a 1, so that's going to give you this point, and then the cosine of pi halves is 0, and that's going to give you this point. So it only takes you to go from 0 to pi halves. Alright, so here we go. I'm going to go ahead and work this one out. I'm going to square that and get 36 cosine squared theta. This 2 and this 1/2 reduced out. And so I can go ahead and multiply the 1/2 and the 36 and get an 18. That's where this 18 comes from. And then I have this one. Oops, what else did I do? Where did this come from? Oh yeah, remember? Your Calc 1 teacher and Calc 2 teacher said you need to remember the half angle identity. So from here to here is the half angle identity. Half angle. We'll just write the whole darn word up. So you substitute that in, and that's where this 1/2 comes from that reduces to give you the 18. And now we just have to integrate this. Well, I'm not going to do substitution for that. If you don't know that by now, shame on you. We talked about that enough in Calc 2, and you're going to see it more in DE if I see you that far. Alright, so the integral of 1 is going to be a theta. The integral of this is going to be, when I do substitution, 1/2 sine 2 theta. So I just need to plug our boundaries by the fundamental theorem of calculus into that, and I end up with 18 times this pi halves plus 0 minus 0, which gives us, oh my goodness, it's the same answer as what we're supposed to get. Amazing. So, Andrea, Mr. Monotone, there you go, boy. Alright, so the next one we need to focus in on, so I think I'm going to zoom as much as I can right here. I can't zoom too much because it'll go away. We're supposed to do the area inside the rows, and I graphed it for you. I think I did an awesome job, let alone the fact that I had to freehand that thing. And so again, what I want to do is I just want to figure out what that's going to be from, I can't use green, from here to here. I want to worry about this portion, and that's it. And then by symmetry, besides this, if I can find this area, I've got 1, 2, 3, 4, 5, 6 of them. That's where that 6 comes from. But I'm going to do 6 times whatever the area is for that little piece that you see right there. If you don't get greedy, it's much easier to just work with those small pieces instead of trying to plug in the big monster thing that you'd have for that equation. Just use symmetry. That's why I talked about symmetry. Alright, so again, remember the formula. So we have the symmetry, and we have 1/2, and this is going to be our radius squared, d theta. And so the boundaries, well, 0 is an obvious boundary because it's going to be the one that's back here. What I have to find out is this one, And you say, well, how did you get this? This is how you got 0 for that, is you solved this equation. And yeah, I did. I solved that equation, but it was pretty daggum obvious that the sine of 0 is equal to 0. But it's the other one. It has to do with the axis of symmetry and where the first petal is at. If you recall our discussion of roses, you take 90 divided by 3 and you get 30 degrees, and that's going to be this axis of symmetry that you have. So I'm using the graphing that we talked about. And so I'm just going to set it up and get used to it. There's a lot of them I'm just going to let you just get away with setting up. And I have my reasons for that, but partly is time, but there's some other reasons as well. Alright, I'm trying to get everything on there so you can see it. Alright, the next one is your lemniscate, and that lemniscate's going to look like this. And again, all I care about is just this one piece. And if I can do that, if I find the one piece, people are texting me, I have 4 of them, so that's the symmetry. There's the 1/2. I'm starting to put it on the outside of the integral. And then how come you didn't square that, Soash? Well, because that's an r squared. So why would I square something that's already an r squared if that's supposed to be an r squared? Again, looking at that formula, if it's supposed to be an r squared, why would I put this thing in and square it? I'm talking about this thing, since you can't see what I'm pointing at. So when I set this up, here's pretty much what your setup is going to be. Oh yeah, how did I get the pi force? Well, I forgot to talk about that. I did something in trig where I solved an equation by substitution. Oh my goodness, you thought you'd never do that again. So I get cosine 2 theta is equal to 0. I do substitution. I figure out that the angle for the substitution is 90 degrees. I resubstitute and I figure that that's 45 degrees. So it's going to take me from here to here. That's going to be at 45 degrees, or pi force is going to be the angle that's going to put me right back at that location. That's going to rotate from 0 to pi force. Good. There's the setup for that one. Let us keep rolling here. Alright, I need to move this so you can see it. And what I want you to recognize here now, if I draw a representative sector, this is going to be a situation where I have, actually this is the thing that's called a polar rectangle now that I think about it. It was coming, I just did it a little too soon. That other thing was a representative sector. This is a polar rectangle. I'll be darned if I'm going to re-record this whole thing because I said the wrong thing before. I'll fix it now. So what we have to do basically is find a bigger area. See if I can color this in. So if I do the bigger area, I think I need a really light color. The bigger area is this whole thing right here. And then I have to subtract the smaller area, which is going to be this part right here. And so what you see here is the formula, and that's any time that you find the area of the region that is outside of one and inside the other. So let me talk to you about that here. When you look at the shaded region, this is going to be outside of the cardioid. So it's outside the cardioid. I need to get a different color so I can write it. So when we're finding this area, it's outside the cardioid and it's inside the circle. So here's the circle and it's inside that and it's outside of this cardioid. So that's the part that we have to do. Anytime that you have that situation, you're having a case that is going to be subtract one sector, the big sector minus the little sector, and it turns out to be this. So anytime you have outside one shape and inside the other, this is the setup that you're going to follow every single time. So what you have to figure out, okay, I'm going to do this by symmetry. I'm going to do the top half right here. And what I'm going to do is then I have 2 times because I have to do the top and the bottom. And I have my 1/2. Then I have my outer radius, which is going to be the circle. Okay, So it's going to be the circle. I'm afraid to erase anything. So I'll have that minus the inner one, which is going to be the cardioid. And I have to square each of those, which is what I did. And there's your setup for anything that is outside of the cardioid and inside of the circle in this particular example. All right, here is another one that is similar to this. You might say it's not outside one and inside another, and they don't quite use that same terminology. Well, yes, they do. I guess I just lied. It's inside the circle, and it's above the line, so it's kind of outside of the line. So we need to find this intersection point, and this is what I did right here. So I set the r values equal, and I eventually end up with sine of theta is equal to half, or cosecant of theta is equal to 2, and that's going to be at pi sixth. So that angle right there is pi sixth, and I don't think there's any question if I do symmetry that it's going to stop at pi halves. And this area that we have, if I color in with a light color, is the area that we're looking for. Color. Stop. This is the area we're looking for, this entire area. I hate that. Alright, so we have to do the outer one minus the inner one. So here's the outer one, here's the inner one, if you want to think of it that way. And if I highlight things then, the 2 is because of the symmetry, the 1/2 times the radius squared times the angle. And the outer radius is going to be the circle, so that's 6 squared. And the inner radius is going to be the line. And oh yeah, by the way, why is that graph a horizontal line? I wonder if you remember from our discussion on the other videos. This is the same thing as 3 times 1 over sine. And if you multiply by sine to both sides, you end up with this, which is like the horizontal line, y equals 3. You're supposed to remember that from the videos that I reviewed. So your setup is going to be from pi sixth, that's going to be your lower boundary, to pi halves is your upper boundary as you rotate this counterclockwise. Alright, let's keep going. I'm convinced I'm going to do 4 videos today, and it's 9 o'clock. Just want you to know what's going on around here. Alright, we have a new situation, okay? When it's shared, and I try to draw the 2 shapes for you as best I can, but what you've got to notice here, and I don't want to destroy anything, so I'm going to do this with a very light yellow, okay? This region right here is going to have a boundary that is going to be the circle. The circle is the green one. And then the other one, that's going to have a boundary for this part. Oh, stop. Give me a color. That is going to be this orange one, and the boundary is going to be the cardioid. It changes boundaries. So when you're looking for the shaded region, the common region, this is different than outside one and inside another. This is the part that overlaps. You're going to always break it up into a format that's going to look something like this. And that color is too weak for what I want to say. So I'm giving you a cookbook situation. Inside one and outside the other, you're going to do this kind of subtraction thing right here. And if you have shared, then you have to break it up because it's going to change behavior. It's going to change boundaries right there. And where is that? Well, I did the trig right here to figure that out. So hopefully you remember how to solve these trig equations. And you say, well, why didn't you do the other angle? Why didn't you do the one that's over here? Well, I don't want that because I'm going to use symmetry. I'm only working on that one side. So if you examine what's occurring for this one, it's going to go from negative pi halves to negative pi sixth. And it's just going to be that circle equation, which is 3 squared d theta. When I go to the cardioid, it's going to go from pi sixth all the way down here to pi halves to finish that cardioid. How do you know that? Because we graphed all those polar graphs that I reviewed with you. Okay, you can't forget stuff. and most of you probably don't remember it from trig. And this is going to go from negative pi halves, or pi sixth, all the way to a positive pi halves. And again, it's 1/2. I forgot to put the 1/2 on the outside, but it's okay. And then I have my cardioid quantity squared d theta. And there's your setup. All right, one more before I take a break. Please notice that this is definitely one that you're supposed to set up. And if you're saying, how come? It's because look at the work you had to do to solve this thing. This is not even one we can figure out what the special angle is. It's one that we have to use the inverse cosine notation. So I'm solving for cosine 2 theta. 2 theta is equal to this because I don't know what the heck the angle is, and I'm not going to get a calculator out and write that in decimal numbers and rating measure. There's no way you're going to make me do that with a calculator right now. And so I have to divide by 2 or multiply by 1/2, so that's what theta is equal to. Now I try to highlight very lightly, if you can see that gray line right there that's dotted, because you have a boundary that is the circle for a while, and then it changes to the lemniscate between that location, which is this ungodly theta that we found down here. Now, how many of those pieces do you have where it's shared? You've got 1, 2, 3, 4, and that's why I'm using symmetry right there. And so I have to do the first one, which is going to be 1/2, 0 to this weird angle, and it's going to be 1 squared d theta. And then I'm going to do it from the weird angle right here up to, and what is it going to take for me to get to that lemniscate that is going to give me that point that's going to be at the pole, and it's going to be pi halves. Don't believe me? Then plug it into this, and I will bet you the farm that you're going to get a 0 for that. R squared equals 0. Mr. Monotone that. All right, then here notice that the R squared is a lemniscate, so you don't square this thing. Don't you dare square that thing. And so there's the setup, and I think I am done. Hot diggity dog.